I think what I discussed last class is about the. So, this is basically what we wanted to show is that this two mode, any two mode. So, any two mode Gaussian state, let us say rho a b, is separable if and only if this rho a b T b is greater than equal to 0, just like in the case of 2 qubit, right. This is what we wanted to prove. So far what we discussed is that, I mean, the uncertainty relation for rho a b, whether Gaussian or not, it does not matter. Okay. This is Gaussian or not, non Gaussian, it does not matter. So, this we have proved that the covariance matrix for the state rho a b plus iota by 2 omega greater than equal to 0, this is the uncertainty relation. Then we have shown that uncertainty relation for rho a b T b, whenever rho a b is separable. So, this is gamma plus I by 2 where this lambda is the the partial reflection, right. So, which is diagonal of 1, 1, 1 and minus 1, right. So, again nothing is there whether this is Gaussian or not. So, therefore, for a two mode state, if it is separable, so if rho a b is separable, then number 1 gamma plus iota by 2 omega greater than equal to 0 and number 2 gamma plus iota by 2, this is greater than equal to 0. So, this is necessary condition. This is necessary condition for separability, right. Then we said that look, this is not very useful, because every time you will have to find out this gamma and all that. So, how to represent it in local symplectic invariant forms. Right. So, this is what we discussed, and then we said that look, this is a one can prove that this one corresponds to, okay. So, basically you should take this gamma, I can always take it A C C transpose B, where A and B are positive matrices, positive definite matrices, real 2 by 2 matrices, and C is also 2 by 2 real matrix. So, this is my covariance matrix. Then we said that this can be written in this form, determinant of A, determinant of B, and then there are these other expressions. Let me write them. So, this is the expression determinant of A plus determinant of B plus 1 by 4 minus determinant of C square minus trace of A j, C j, B j, C transpose j greater than equal to 1 by 4 determinant of A plus determinant of B, right. So, this is what we said, that it can be proved that this condition in this local symplectic invariant form will become this. We have not yet well, I think I gave some argument why this is the case, and this one will correspond to determinant of A, determinant of B times then plus 1 by 4 plus determinant of C square minus trace of A j, C j, B j, C transpose j greater than or equal to 1 by 4 determinant of A plus determinant of B, right. Okay. So, therefore, the necessary condition for separability of rho A B of any two mode state, rho A B is this one, determinant of A times determinant of B then plus 1 by 4 minus magnitude of determinant of C whole square minus trace of A j, C j, B j, C transpose j greater than equal to 1 by 4 determinant of A plus determinant of B, right. This is the necessary condition for separability of this. Okay. Right. Now, the question is how to prove this thing. I think we have given argument that you take any covariance matrix of a two mode state A, C, C transpose B, then by local symplectic transformation S local, okay. By local symplectic transformation you can, so local symplectic is this one S1 0 0 S2, where this S1 and S2 are SP2R. So, by local symplectic transformation you can bring it to this form where A is A0 0 A and the C is C1 0 0 C2, again C transpose is C1 0 0 C2 and B is B0 0 B. Of course, because this is a covariance matrix, so A and B must be greater than or equal to half, this we have already discussed, and in principle you can, and C1 and C2 these are real numbers of course. Okay. So, this I can always do. In particular you can also take that A is greater than equal to B greater than equal to half and C1 is greater than equal to C2 greater than equal to 0. This I can always do. Okay. So, this part of course, this is easy, this part, right. I mean it does not matter which one is you take greater, here or here, it does not matter, but this part is one can also prove that this is the case. So, I will discuss about that. So, by local symplectic transformation you can bring this into this form. This is a canonical form. This is not the only canonical form, but this is a useful canonical form. And then what we said is that, so let me call it as gamma 0 is a canonical form. So, then we said that the condition, so the uncertainty relation for gamma 0, okay, and you see that gamma 0 is S local gamma S local transpose, right. And because this is a similarity transformation, you know, gamma. So, this gamma plus iota by 2 omega greater than equal to 0, this will imply that gamma 0 plus iota by 2 omega also greater than equal to 0, right, because under symplectic transformation this property should not change. Okay. Now, if I want to figure out, so basically what you need to look at is this matrix A iota by 2 minus iota by 2 A C 1 0 0 C 2 C 1 0 0 C 2 B iota by 2 minus iota by 2 B. This is the matrix and you will have to prove that this is greater than or equal to 0. So, as I said, you can write down the eigenvalue equation for this matrix and you can show that the corresponding condition is like this. So, let me yes. So, this I mean this positivity is equivalent to this one A square B square. As I said, you look at basically the positivity of the determinant of this, that is enough. So, A square B square plus 1 by 4 minus C 1 C 2 square minus A B C 1 square plus C 2 square greater than or equal to 1 by 4 A square plus B square. Okay. This is the positivity condition. And now, if you look at this, so let me call this as your I have called it A. So, let me call it as A 0. So, all of them are 0, right. So, then you see that this is equivalent to A square is determinant of A 0, then B square is determinant of B 0 plus 1 by 4 minus C 1 C 2 is determinant of C whole square C j B j C transpose j, this is this quantity. So, this quantity is same as this one and then this is greater than or equal to 1 by 4 determinant of A plus determinant of B. Okay. I mean A B means well I should put here C 0, A 0, C 0, B 0, all of this 0. Huh? Okay. So, you see that positivity of this condition, that means this condition is equivalent to this condition, right, because positivity of this demands this one and in particular this case it is this, okay, right. And then we said that look, the original A and this A naught, how are they related? So, A naught is equal to S 1 A S 1 transpose, right. B naught is S 2 A S 2 transpose, C naught is S 1 C S 2 transpose, right. And then all of this will imply that trace of A 0 j C 0 j B 0 j C 0 transpose j, this is equal to trace of A j C j B j C transpose j. Okay. And from here you can figure out that determinant of A 0 is same as determinant of A, determinant of B is same as determinant of B 0 and determinant of C is same as determinant of C 0, because these are symplectic transformations. So, their determinant is 1. So, you see that basically this condition is same as this condition what I have written here. What is that? So, this condition is same as, let me write it down, determinant of A, determinant of B, and then plus 1 by 4 minus determinant of C whole square minus trace of A j, C j, B j, C transpose j greater than equal to 1 by 4 determinant of A plus determinant of B, right. So, this means that the uncertainty relation. So, if you can prove uncertainty relation for this matrix, it is equivalent to proving uncertainty relation for this matrix, right. In the same way, if I can prove uncertainty relation for let me erase this part. So, uncertainty relation for rho A B T B, okay, where rho A B has covariance matrix gamma 0, right. So, then this will tell me that gamma 0 plus iota by 2 omega tilde greater than equal to 0, where omega tilde is lambda omega lambda, which is basically I sigma y 0 0 minus I sigma y. Sigma is, I mean the omega is I sigma y 0 0 I sigma y, right. So, this is the uncertainty relation for that covariance matrix. And now, if you express in terms of the eigenvalues etc., what it will come is the same thing, A 0 determinant of B 0 plus 1 upon 4 minus determinant of C 0 square, then minus trace of A 0 j, C 0 j, B 0 j, C 0 transpose j greater than equal to 1 by 4 determinant of A 0 plus determinant of B 0, right. Here this should not be minus, it should be plus, right, because you understand that how this under partial transposition how this changes, determinant of C will go to determinant of minus C, okay. And this again, you know, this is equivalent to, so I can replace this. So, because you know this is equivalent to determinant of A into determinant of B plus 1 by 4 plus determinant of C whole square minus trace of A j, C j, B j, C transpose j greater than equal to 1 by 4 determinant of A plus determinant of B. Why? Because as we have discussed, determinant of A 0 is same as determinant of B, determinant of B 0 is same as determinant of B, so on and so forth. Okay. So, therefore, this completes the proof. What I have written earlier, the necessary condition for separability of any two mode state is basically this one, with this being replaced by minus magnitude of this, right. Okay. Fine. Right. So, the next thing is that what we also discussed is about the sufficiency. Necessity is fine. What about sufficiency of this condition? So, you see that this is this condition rho a b T b is greater than equal to 0, I mean sorry rho a b T b, this is actually equivalent to this. Okay. So, this is the basically what we wanted to prove, and then for Gaussian states we said that yes. So, the sufficiency says that if for any two mode Gaussian states rho a b having covariance matrix gamma is equal to A C C transpose B, we have determinant of A times determinant of B plus 1 by 4 minus determinant of C mod square minus trace of A j C j B j C transpose j is greater than equal to 1 by 4 determinant of A plus determinant of B, then rho a b is separable. Okay. So, this is the sufficiency condition for separability, just like in the case of 2 qubits. So, positivity of this implies that the 2 qubit state is separable, right. Okay. And how do we go about this? So, let us take this case 1, the determinant of C is negative, right. The determinant of C is negative. Okay. Okay, good. So, yeah. By the way, I have assumed here that so what we can do is without loss of generality, assume that all the means are j rho 0, okay, for j is equal to 1, 2, 3, 4, where r is this vector, right, x 1 p 1 x 2 p 2. So, I have see, because for separability this does not matter, because even if this is non-zero, I can do the displacement, individual displacement, local displacement to make it 0, and that will not change the separability criteria. Okay. So, I will assume that these mean values are 0, right. Okay. So, here what okay. So, here of course, I said that uh, yeah. So, again I am not going to prove it for general covariance matrix. So, I will prove it for gamma 0, which is A 0 0 A, C 1 0 C 2, C 1 0 0 C 2, B 0 0 B, where you can take A greater than equal to B greater than equal to half, C 1 greater than equal to C 2 greater than equal to 0. This I can always choose, and you see that as I told you that it does not matter whether I do it for this one or for the original one, because under local symplectic transformation it will not change the separability property. It can change classicality of the state, but does not change the separability property. Okay. So, without loss of generality, so this is what I am going to use. So, this is my A, this is my C, this is my B, and this is of course C transpose. Okay. So, I should have written here C 0 etcetera, but that is okay, right. Okay. So, no, maybe let us start with this one and then we will do that, because this case is easier. So, what I will do is I will take determinant of C positive. Okay. Oh, sorry, this is my sorry. Yeah. So, this is the proof. Of course, I will have to prove this, but this is the main result. Okay. I mean, so what I will do is I will prove it step by step. Okay. So, not directly going into the proof. So, I will prove it step by step. Okay. So, ultimately that is the result we will have to prove. So, the thing is, what we need to prove is the following, that so this is a lemma. It says that if gamma is equal to A C C transpose B is the covariance matrix of a two mode Gaussian state, rho 1 2 or rho A B with mean zeros. Okay. So, mean zeros you understand, right, this is what we have assumed, and if determinant of C is greater than equal to 0, then rho A B is separable. Okay, maybe I should use 1 2 because here we have A B. So, maybe I should use 1 2, otherwise it is a bit confusing. So, you understand that this is mode 1 and mode 2. Okay. So, this is so basically it tells you that if this is a covariance matrix of a two mode Gaussian state where determinant of C is greater than equal to 0. See, A and B are already positive matrices, half identity 2 plus 2, these are already positive matrices, these we know by uncertainty. But on the top of that, if this is greater than equal to 0, then this is separable. Okay, for a two mode Gaussian state, not for arbitrary state, but for two mode Gaussian state, this is what is going to happen. Okay. Now, as I said, So, without loss of if I want to prove this, so without loss of generality, we can take this gamma is equal to gamma naught is equal to A 0 0 A, C 1 0 0 C 2, C 1 0 0 C 2, B 0 0 B with, as I said, you can take this A greater than equal to B greater than equal to half, C 1 greater than equal to C 2 greater than equal to 0, right. Okay. In fact, this is of course true, and for this, even if this is not the case, you can do little bit of local symplectic transformation, little bit of trick to make it. So, for example, let us say C 1 is less than C 2, then what you do? You apply these this transformation S local is equal to sigma x 0 0 sigma x. This is also a local symplectic transformation, and that will basically interchange the position of C 1 and C 2. Okay. And if C 1 and C 2 are, so because of this condition, either C 1 and this is satisfied, or both C 1 and C 2 are negative, so that their determinant is positive. So, in that case, again you can apply this thing like I think it is sigma z 0 0 sigma z, something like this, you can apply to make it all positive. So, this is simple, you can do that. Okay. So, therefore, without loss of generality, you can assume this, and then okay. So, what do we want? Basically, I want to bring this in a form which is like diagonal, something like this, kappa plus prime, kappa minus prime. So, which is kind of, it is not this, what is that called, Williamson's form exactly, because in Williamson's form these two are same and these two are same, but the idea is to bring it in this form, and then to check whether the state is classical or not will be easy, and once you find out the state to be classical, separability is automatic, right. So, this is what the idea is. Okay. So, what is it that you need to do? So, let us take this thing, step 1. So, you apply this S local, which is S 1 is diagonal x and 1 by x, this is 0, this is 0, and this is diagonal 1 by x and x. So, where x is a positive number. So, what am I doing? I am applying squeezing on the first mode and anti squeezing in the second mode, right. Is it clear? Yeah. So, if you do that, then your gamma 0 will go to gamma 0 tilde, which is S local gamma 0 S local transpose, and this if you calculate is easy, is not difficult. Okay. So, if you calculate, this will be A x, because only the diagonal entries will be affected, off diagonal will not be affected, A x square 0 0 A by x square, then this is C 1 0 0 C 2, C1 0 0 C2 and then this is B by x square 0 0 B x square. Okay. So, what have I done? So, I have not done much, I have just used this squeezing in the first mode and anti squeezing in the second mode, reverse scaling. Okay. So, this is how we get. So, this I call as gamma 0 tilde. Now, under this transformation, if original state was separable, this has to be also separable, right, because this is local symplectic. If the original state is Gaussian, because this you can realize by Gaussianity preserving transformation, because squeezing is a Gaussianity preserving transformation. So, the state corresponding to this covariance matrix will also be Gaussian. Okay, right? Okay, good. So, separability does not change, separability or entanglement nature, amount of Gaussianity might change, but the Gaussian nature will not change by this local symplectic transformation. Okay. So, next step is step 2, you apply the same local squeezing. So, this is maybe I will call it as S local. So, this is maybe I will call it as 1, this is 1 1 and then this is S local 2, which is diagonal of y 1 by y 0 0 diagonal y 1 by y, again y is a positive quantity. So, you are applying the same squeezing on both the modes, right. So, then your gamma 0 tilde will go to let us say gamma 0 prime, which is S local 1 2, then well I should not put this, it should be, because otherwise okay. So, S local 2, then this is what was the original one, it will go to gamma 0 tilde S local 2 transpose, okay, right. So, again if you can calculate, this is again simple, but this time there will be change in the off diagonal entries. So, this will be a x square y square 0 0 a by x square y square, this is fine. Now, this time it will be c y square 0 0 c 1 y square c 2 by y square, this is c 1 y square 0 0 c 2 by y square, and here it is b y square by x square 0 0 b x square by y square. Again, if the original one is, because this is, if this corresponds to a separable two mode state, this will also correspond to a separable two mode state, because local symplectic transformation. If this is classical, this will also be classical, right. Well, no, sorry, if this is Gaussian, this will also be Gaussian, classicality might change. This is Gaussian means this is also Gaussian, because this is Gaussianity preserving transformation, okay. Classicality might change, okay, good. Now, we have two parameters x and y. So, we will have to choose x and y in such a way that we will get this, but we are still a bit far from getting this version. So, the next thing is this one, and this is crucial. So far as we have seen, these two transformations are local symplectic transformation, Gaussianity preserving, and also it does not change separability. So, next step is, this is a crucial step. Now, you apply rotation between the modes, same rotation between the modes. Okay. So, what is that? So, you say S 3, I will call it theta, So, this is cosine theta 0 sin theta, then 0 cosine theta 0 0 sin theta minus sin theta 0 0 minus sin theta, this is cosine theta 0 0 cosine theta. So, what is it going on? This is your x 1 and p 1, this is x 2 and p 2, here also x 1 p 1 x 2 p 2. So, if we look at this rotates, oh sorry, no, not this one, sorry. I mean, if you take this one and this one. So, this tells you that x 1 p 1 it goes to cosine theta sin theta minus sin theta cosine theta x 1 not p 1 x 1 x 2 x 1 x 2, right. And similarly, x p 1 p 2 it goes to so this one and this one. So, this is cosine theta sin theta minus sin theta cosine theta, this is p 1 p 2. Is this clear? So, what is happening is you are basically rotating in the between. So, this is rotation between the two modes, same rotation, these and these are same rotation between the two modes, right. Now, is this a canonical transformation? Of course, you can figure out that this is a canonical transformation. Can it be achieved by local symplectic transformation? No, because it is mixing between the modes. So, it cannot be achieved by local symplectic transformation. Is it a Gaussian transformation? It will be, I will show you. But if it is not local, what is the guarantee that it will not change the separability or entanglement character of the state, because it is not local, okay, right. Yeah. So, we will show that if the state is classical to begin with, under such a transformation it will remain classical. If the state is non-classical, under such a transformation it will remain non-classical. Okay. Separability might change, but I mean in fact here it will not, but classicality will not change. Okay.
It implies that separability will not change.
Yes. Okay. So, now what is this transformation? This is very familiar transformation, if I do this thing between the modes. So, let us say I have the modes A 1 and A 2, these are the annihilation operators of the modes. This goes to cosine theta sin theta minus sin theta cosine theta A 1 A 2. Okay. And what is it? This is the beam splitter transformation. Okay. So, this is the beam splitter transformation, right. And we know that under beam splitter transformation a classical state will remain classical state, a non-classical state will remain non-classical state. Okay. So, this is a beam splitter transformation, right. So, this you can write as, this is cosine theta identity 2 cross 2 sin theta identity 2 cross 2 minus sin theta identity 2 cross 2, cosine theta identity 2 cross 2, right. I mean if you take this one and this one. Okay. So, this is what you will have. Okay, good. So, now what I want is what was our, this is gamma 0 prime. So, what we want is to see this gamma 0 prime will go to, let me call it as gamma 0 double prime, which is S 3 theta gamma 0 prime S 3 theta transpose, right. This is the transformation you will have. Okay. I will just write for you I mean although this is too big, so maybe I will write here. So, this gamma 0 double prime, it will have the following form, cos square theta diagonal of a x square y square comma a by x square y square plus sin twice theta into diagonal c 1 y square c 2 by y square, then plus sin square theta diagonal b y square by x square comma b x square by y square. So, this is the first half, and then this is too much, minus half sin 2 theta diagonal of a x square y square comma a by x square y square plus sin half sin 2 theta diagonal b y square by x square comma b x square by y square minus sin square theta into diagonal c 1 y square c 2 by y square and plus cos square theta into diagonal of c 1 y square c 2 by y square, and of course, the same thing will be here, same. Okay. And this one will be sin square theta into diagonal a x square y square a by x square y square plus cos square theta into diagonal of b y square by x square b x square by y square minus sin square theta, I think, or sin 2 theta diagonal of c 1 y square c 2 by y square. Okay. Right. I mean, I guess it is correct, but anyway, this is a straightforward calculation, nothing serious is there. Okay. So, now what we want, because I said that this has to be a diagonal one. So, I want this part, which is a diagonal matrix, to be 0. This is my demand, and therefore, this should also be 0, because it is the same. Okay. So, if you demand that, I am not going into all those calculations, you can figure out that yes. So, from here what you will figure out is the following, that C 1 by a x square minus b by x square is equal to C 2 by a by x square minus b x square. Okay. So, if I demand that this is 0, then well no sorry sorry it is this is fine, I think this is 0, yes, yeah. Yeah, so anyway, so basically what we want is that these okay, maybe I should not write in this way. So, so this demand that this should be 0. Okay. So, this will lead you to this condition that, so this demand, this will lead you to this one, I think C 1 by a x square minus b by x square is equal to C 2 by a by x square minus b x square, and this will give you value of x. Okay. Because if you solve it, it will give you some value of x. I think this x is, let me see whether, yeah. So, x is this one, C 1 a plus C 2 b by C 1 b plus C 2 a whole to the power 1 by 4. Okay. So, this is what this demand will tell you, and also it will give you this condition that tan twice theta, or maybe I should not write tan twice theta, twice C 1 by a x square minus b by x square into cos 2 theta is equal to sin 2 theta. Okay. And this will provide you what is, so this will provide you tan 2 theta, I think this is equal to 2 times square root of C 1 a plus C 2 b, C 2 a plus C 1 b whole divided by a square minus b square. I mean, one should be careful, because I have assumed a greater than equal to b. So, this can be 0, in that case tan 2 theta will be 2 theta will be what, pi by 2, right. Yeah. So, this is the kind of thing you will get. Okay. So, in fact, yeah, and then you can figure out. So, with this, with the help of this, you can now figure out that this is equal to diagonal of kappa plus prime, kappa minus prime, because ultimately it will be diagonal, right. And then you can write down this kappa plus minus is equal to y square by 2 a x square plus b by x. Of course, you will have to put the value of x, which I have not yet put here. So, this is a x square minus b by x square whole square plus 4 c 1 square whole to the power half, and then this is kappa plus minus prime is equal to 1 by 2 y square a by x square plus b x square plus minus this is a by x square minus b x square whole square plus 4 c 1 square of yes. So, these are the solutions, okay. And you can see that both all of them are non negative, okay. So, this you can check, this all of them are non negative, right, okay, good. So, now you have this diagonal form, all of them are non negative. So, let me erase this part, and so the free parameter is y, x is of course known from here. Okay. Okay, so I said that beam splitter transformation does not change the classicality or non classicality nature of the state, right, because beam splitter is a passive transformation, and you know so if I take the state rho a b having p distribution like alpha 1 alpha 2 belonging to C d square alpha 1 d square alpha 2 p rho alpha 1 alpha 2. I am not assuming that this is non negative, it can be non negative everywhere, it may be singular also. So, this is alpha 1 tensor product alpha 2 alpha 2, this is my state, right. And now, if I apply this unitary which is S free theta, okay, so which is the beam splitter transformation on rho a b u S free theta dagger, right, this is how it will change. So, you will see that what will be the corresponding representation. So, this will be alpha 1 alpha 2 belonging to C d square alpha 1 d square alpha 2 p rho alpha 1 alpha 2. You will have to look at the change here. Now, how is it changed under the beam splitter transformation, namely where a 1 a 2 goes to cos theta a 1 plus sin theta a 2 and then minus sin theta a 1 plus cos theta a 2. So, this is my beam splitter transformation which corresponds to S free theta, that is what I have taken. So, this will go to basically you will have to give the. So, this is in the Heisenberg picture. So, in the Schrodinger picture what you will get is the following. So, alpha 1 cos theta minus alpha 2 sin theta. So, this is at the state level. Okay. So, the inverse of this rotation it will have alpha 1 cos theta minus alpha 2 sin theta, and then this is alpha 1 sin theta plus alpha 2 cos theta, alpha 1 sin theta plus alpha 2 cos theta. Okay. So, this is how the state will change, right, because this is the beam splitter transformation, right. And now, let me call these as alpha 1 prime and this as alpha 2 prime, right. This is a rotated version. Now, because this is in a rotation in alpha 1 alpha 2 plane, this does not change the Jacobian of the transformation. So, I can take it alpha 1 alpha 2 prime belonging to C, d square alpha 1 prime, d square alpha 2 prime, p rho. Now, I replace alpha 1 alpha 2 by alpha 1 prime alpha 2 prime. I can always do that, right. I mean basically I express alpha 1 in terms of alpha 1 prime and alpha 2 prime, alpha 2 in terms of alpha 1 prime alpha 2 prime. So, therefore, let me call these as p tilde alpha 1 prime alpha 2 prime. So, this is actually same as this, these two are same, only thing is I am re-expressing it in terms of alpha 1 prime and alpha 2 prime, and this multiplied by alpha 1 prime alpha 1 prime, then alpha 2 prime alpha 2 prime. Is this clear? This does not change the Jacobian, because this is a rotation. Okay. Well, Jacobian will be basically the 1. So, what you see is that under such a beam splitter transformation, the state will change of course, but it will not change the character of classicality non-classicality, right, because this is again a coherent state representation. If this is everywhere non-negative, this is also everywhere non-negative and vice versa. So, therefore, this is classical equivalent to this is classical. Okay. So, it does not change, I mean you can say classical non-classical. So, it does not change the classicality or non-classicality property of the state under this beam splitter transformation. Okay. This is what I just said, right. Okay. So, the two mode Gaussian state, if it was originally separable, I mean it was originally classical, it will remain classical. Is that clear? Okay. Now, of course, you see that for this is my, so this is your gamma 0 prime, this one, and because this is a bona fide covariance matrix. So, I know that k plus kappa plus prime greater than equal to 1 by 4, kappa minus prime greater than equal to 1 by 4, right. This is because this is bona fide covariance matrix. Okay. So, this is of course true. Okay. And of course, you know I can arrange them, it is not a problem. I mean I can take them to be like this. Yeah. So, I can take here. So, this is in the first mode and this is the second mode, right. So, in principle I can choose kappa plus is greater than equal to kappa minus, no problem in that, and similarly kappa plus prime is greater than equal to kappa minus prime. I can always do that, right. I mean basically you will have to give a preference to the modes. So, that is up to you. Now, I have still these free parameter y. Okay. I have not yet chosen free parameter. So, now what I do? I choose this y in such a way that these two become equal, kappa minus and kappa minus prime, they become equal. So, basically you choose y such that kappa minus is equal to kappa minus prime. Okay. Right, and this will provide you what is the value of y. So, Yeah, I do not want to write the value of y, you can figure out, find y, what is y if you do this thing. Okay. So, once you have these that they are same, so then what is the condition for uncertainty? So, kappa plus is greater than equal to kappa minus, that we have taken, and this we know that this is greater, this has to be greater than equal to half because of the uncertainty. Similarly, kappa plus prime is greater than equal to kappa minus prime, which is equal to kappa minus, which is also greater than equal to half, right. Okay, good. So, what do you have now here is that your gamma 0 double prime, which is equal to diagonal kappa plus prime, kappa minus prime, which is greater than or equal to diagonal of half, right. Okay. This is what is happening, right. So, this is your basically half identity 4 cross 4, right. This is greater than equal to identity 4 cross 4, right. Okay. So, now let me go back. So, remember we obtained this gamma 0 double prime from gamma 0 prime, right. In fact, this is equal to S 3 theta gamma 0 prime S 3 theta transpose by the beam splitter action, right. And this is a rotation S theta 3, this is a rotation in 4 dimension. It means that this is an element of SO4, right. So, this is a similarity transformation, because this is greater than equal to 1 by 4 identity. This will automatically imply that gamma 0 prime is also greater than equal to 1 by, not 1 by 4, 1 by 2 identity, right, because this is a rotation. So, the same character will remain there, eigenvalues will not change, right. Now, if this corresponds to a 2 mode classical Gaussian state, if this corresponds to a 2 mode classical Gaussian state, then this also corresponds to a 2 mode classical Gaussian state. Why? Because under beam splitter action, that classical nature will not change, and Gaussian nature will also not change, because beam splitter action is a, it is generated by quadratic Hamiltonian. So, Gaussianity property will also not change. So, if this corresponds to a 2 mode classical Gaussian state, this will also correspond to a 2 mode classical Gaussian state, okay, right. Okay, good, fine. And next, how did we get this gamma 0? I mean, I got this gamma prime from gamma 0 by again local symplectic transformation, right. In step 1 and step 2, we assume local symplectic transformation. So, this is S local gamma 0 S local transpose, which corresponds to basically squeezing, okay, local squeezing. Okay. Right. Now, so let us say that the state that you obtained, so the two mode Gaussian state corresponding to the covariance matrix gamma 0 double prime, which you have obtained. So, let us say that this is classical, let. Okay. So, then this state, so this state, it should be of this form alpha 1 alpha 2 d square alpha 1 d square alpha 2 p of, I am not writing alpha 1, so just p of this alpha 1 tensor product alpha 2 and this is non negative. For all alpha 1 alpha 2, right, this is classical. From here, if I apply this, because this we have obtained by this beam splitter transformation. So, therefore, the state, so which we have obtained from the beam splitter transformation, this we obtain after the beam splitter transformation. So, that state should also be classical, Gaussian and classical. Is that clear? This we obtained by local symplectic transformation, like from here. Local symplectic transformation does not change Gaussian character, because this is generated by quadratic Hamiltonian. So, therefore, it came from a Gaussian, and now classicality might change, but local symplectic. So, this classical means this is separable, right, because classical means the state is separable, this is non negative. So, this state is separable. Now, so at this level, so this is at the level of gamma 0 double prime, this is at the level of gamma 0 prime, this is at the level of gamma 0. So, this was from Gaussian, you got this Gaussian, and local symplectic transformation will not change separability property. Okay. So, and separable. So, we are basically reversing the process. So, therefore, if this final one corresponds to a classical Gaussian state, the original one should also correspond to Gaussian separable state, right. Okay. I mean, if the final one corresponds to yeah. So, this is what you have. So, therefore, you see that under all this thing, if you get a classical state after all this transformation, then the original has to be separable, right. Is that clear? Original has to be separable from where you have started, okay, right. So, what we have assumed now so far is that this state, this corresponds to a classical two mode Gaussian state. And this follows, this will follow, we will prove that. So, if you assume that this corresponds to, this is a Gaussian state, that this corresponds to a classical Gaussian state, then the original one has to be a classical, that means the separable one. Okay. So, the question is that what you can now prove is that the okay. So, this is, let me erase this part. So, what we have seen is that gamma 0 double prime is greater than or equal to diagonal half. So, basically this is greater than or equal to half 4 cross 4, right. This is what we have seen, is not it? Yeah, where from this follows, yeah, by where from does it follow that, yeah. So, this is actually, yes, so any two mode Gaussian state with covariance matrix greater than or equal to this will imply the state is classical. So, this is what we are going to prove. Now, this is for the change under this symplectic transformation. Now, as I said, this will imply that gamma 0 prime is greater than or equal to half 4 cross 4, where you got it by this S 3 theta, right, the means filter transformation. Then this will imply, because you have done it by local symplectic transformation. Okay. So, okay. What can I say about this? Yeah. So, this will not of course change the separability property, but it can change the classicality, because under local symplectic transformation it can change the classicality. Anyway, so, but this is fine. So, what we have seen is that gamma 0, this corresponds to, because this is, if this is classical, if this corresponds to classical, Gaussian classical, then we are good that this is Gaussian and separable, right. I am not saying classical. Why separable? Because local symplectic transformation will not change the separability character. So, if this is classical Gaussian, the original one has to be also separable, right, and this is classical means this is of course separable. This will automatically mean separability. So, this is separable, which follows from here. So, if we can prove that for a two mode Gaussian state, if its covariance matrix is greater than or equal to half identity, then it will prove that the state is classical and therefore separable, and from there you can infer that the original state is also separable. Okay. Is this clear? So, we will have to prove this. Okay. So, what we have, so let us assume that this is true, we will prove that. So, what we have proved is that this, so this is what we have proved. What we have proved is that for any two mode Gaussian state having covariance matrix gamma is equal to A C C transpose B is separable if determinant of C is greater than 0, because we have started with determinant of C greater than 0, right, and from there we have proved that this state is separable assuming this. Now, you might say that where did we use this Gaussian nature? Yes, so we have used only Gaussianity here. So, this is where we will have to use the Gaussian nature, nowhere else we have used Gaussian nature. Okay. So, this is where we will have to use the Gaussianity nature. So, if this is positive, then we have proved, assuming this is true, that the state Gaussian state is separable. Okay.
What was this positivity of determinant of C was used?
Yeah, so the C positivity was used in in this condition. So, if you look at this expression for x, what was that? So, we said that in principle you can take C1 greater than equal to C2 greater than equal to 0, right, in this canonical form. Okay. So, therefore, determinant of C can be either 0 or greater than 0. Okay. So, yeah, so I think this x was like this, right, and similarly y will also have some C and other thing, C2b divided by C1b plus C2a whole to the power 1 by 4. So, if this is 0, then C2 will be 0 for example, or both of them can be 0, C1 C2. In that case, you will have to be careful, okay, for this. In fact, for y also you will have this C1 C2 etc. So, anyway, so that will come later. So, this is yeah. Yeah, in fact, when we consider this tan theta, yes, so I do not know, we have written this expression for tan theta. So, I think this is the expression that tan twice theta is equal to, or let us say 2 C1 by A x square minus B by x square into cosine twice theta is equal to sine twice theta. So, from here if you want to get tan theta, and basically your C1 should not be 0, C1 can be 0, if C1 0, C2 is also 0. Okay. So, we have assumed in this case that neither C1 nor C2 0, but you can have also the case where determinant of C is 0, in that case C2 has to be 0. Okay. Anyway, so basically this is what we have proved, and then what is the time now? Yes. So, let me see. And you can now, I will just briefly mention this yeah, this is bit lengthy proof. Okay. So, this the other one, this Duan and all, that is also kind of lengthy, but in their paper they have assumed so many things. Okay. So, let us take this case 2 which is determinant of C is equal to 0, right. See, according to our notation, determinant of C can be either positive or 0, it cannot be negative because of this. Okay. So, in this case, this means that C 1 greater than equal to C 2 is equal to 0, right. Okay. And then what you can do, so therefore, your gamma 0 is A 0 0 A, C 1 0 0 0, C 1 0 0 0, B 0 0 B, of course, your A greater than equal to B greater than equal to half and C greater than equal to 0, that is of course true. Okay. So, you can apply now again this local symplectic transformation, which is like this: diagonal square root of 2a 1 by square root of 2a, and so this is 0 0, diagonal square root of 2b 1 by square root of 2b. Okay. So, this is so if you apply this, so gamma 0 will go to, let us say, gamma 0 prime, which is S local gamma 0 S local transpose. So, this will be of this form: twice A square 0 0 half, then twice A C 1 0 0 0, twice A C 1 0 0 0, and twice B square 0 0 half. So, you see that two of these diagonals I have made half, okay, in order to compare with this half times identity. So, this is what you will have, okay. And then what you do is you perform. So, now you look at the uncertainty relation. Okay. So, for this, if you look at the uncertainty relation, so gamma 0 prime plus iota by 2 omega greater than equal to 0, this is your uncertainty relation. So, again I am not writing what one can get, is what you get is basically this one: A square B square. So, B square minus C 1 square minus 1 by 16 is greater than equal to 1 by 4 A square plus B square minus half. This part is non-negative. Why? Because A is greater than half, B is greater than half. So, half plus half, I mean 1/4 plus 1/4 half. So, this is non-negative, right. So, this is already non-negative, right. Okay. So, and this will imply that these okay. So, this is fine. Now, what you can prove is that, so this condition A square B square minus C 1 square minus 1 by 16 greater than equal to 0, okay, not this one, in fact this condition, sorry. So, this will imply, this you can prove, that gamma 0 minus half gamma 0 prime minus half, this is greater than equal to 0. Okay. Is that clear? So, this is your uncertainty, and from this uncertainty you can prove that this is satisfied. Okay. Right. So, this is your covariance matrix corresponding to a Gaussian 2-mode Gaussian state, because the original one is also 2-mode Gaussian, and there this tells you, according to our this result, that this greater than equal to half for a Gaussian state implies that the state is separable, right. So, this implies that this gamma 0 prime is a separable 2 mode Gaussian state, right. And how did you get it from gamma 0? Gamma 0 prime, how did you get it? By local symplectic transformation. It does not change the separability. So, therefore, and it also does not change the Gaussian character. So, therefore, gamma 0 which is here, it is also a 2 mode Gaussian separable state, right. So, you see that if you assume this condition, then in this case also the corresponding 2 mode Gaussian state is separable, okay, right. So, what we have proved is that this entire result, that if I take a 2 mode Gaussian state with covariance matrix gamma where determinant of C greater than equal to 0, then the state is separable, right. This is what we have proved. So, our result is based on this one, that for a 2 mode Gaussian state, if its covariance matrix is greater than equal to half, then the state is separable. I mean separable means classical and therefore separable. Okay. So, I think today we cannot do, next time I will prove this thing, okay, and then it will be so be done with the job. Okay. Right. Okay. Is that clear what I said? Okay. Okay, then thank you.